Hello, in this video, I'm going to present our paper about blockchain measurement. My name is Hwanjo, and this is a joint work with Professor Seungwon Shin. Before moving on to our measurement, please let me explain how a blockchain is constructed and why we need a measurement. Blockchain is a growing list of blocks. Inside every block, there is a block header and a list of transactions. Then how are blocks produced and appended to this list? Suppose we have a blockchain up to the block number I. As you can see on the right, there is a blockchain network comprising a number of participating nodes. Some of them are user nodes who make transactions. A transaction can be a token transfer or an implication of smart contract code. There are also miners who want to produce blocks. Here, for example, a user node at the center comes up with a transaction, in this case TX3, and deliver that transaction to its peers. Miners listen to this transaction advertisement and put them into its block proposal if it's valid. A miner also comes up with a block header, including the solution of crypto puzzle. If the solution is found, it disseminates the newly produced block to its peers. As you can see here, all blocks and transaction information are broadcast to the entire network, and the final blockchain data structure is validated and stored by every network node. Then why do we need a measurement? Again, the blockchain data is there for everyone. For example, Block Explorer services provide the data, and also you can operate your own blockchain node and query the local database. However, the historical blockchain data is not sufficient for us to fully understand what's going on under the hood. Let's be more specific. We can reconstruct the block and transaction arrival events from the blockchain data in what we call historical view. In the view, there are transaction and block arrivals in the time axis. For example, T sub 0 and T sub 1 are the two transactions included in the block B sub 10. On the other hand, we can observe block and transaction arrival events in measurement view by measurement of their arrivals in the network. What are the differences between them? First, there can be state blocks that are produced and disseminated but not included in the canonical chain. The gray colored events represent arrival events that are not observable in historical view. There are also state transactions that are exchanged in the network but not included in a block. Furthermore, there can be transactions we find in blocks but never observe across the network. And also, as a transaction does not have an individual timestamp, we cannot get a sense of when this transaction is ever initiated. To recap, there are such discrepancies in terms of block and transaction events in two different view models, and that's why we need a measurement. There are a number of related work mostly analyzing the historical transaction data without measurement. There are also measurement-based studies. However, to the best of our knowledge, our work is the first comprehensive study based on transaction and block measurement performed at multiple network locations. For our measurement, we modified the reference implementations of Bitcoin and Ethereum to log all received transactions and blocks. We have deployed our software at 8 network locations of Google Cloud. However, we have encountered a number of problems by which our measurement data is incomplete. We had to deal with those problems very carefully for precise and sound analysis, and you can find the details in our paper. The first thing we've investigated with our dataset is blockchain fork. The fork happens by definition if there are 2 or more blocks with the same height. Blocks that are not included in the canonical chain are called stale blocks. In overall, stale blocks are very rare for Bitcoin. And combining with the numbers reported by previous work, we see that the rate is apparently decreasing. And this can be an indication of absence of selfish mining, even though it is theoretically shown that the selfish mining is profitable in a wide range of circumstances. The graph on the right depicts an example Ethereum fork event, and Ethereum miners are incentivized to put information regarding uncle blocks in their published blocks. Our measurement captures stale blocks that are not uncle blocks as well. One interesting finding we've made regarding blockchain fork is that widely used assumption by mining research is not realistic, at least for Ethereum. The assumption states that honest miners add blocks to the earliest propagated blocks if there is a fork. For example, the right side figure shows that there are 3 blocks with the same height, from B sub 1 to B sub 3, that are added to the block B sub 0. Miners have to choose to work on a new block, referring one of the 3 choices of B sub 1, B sub 2, or B sub 3. A rational choice for honest miners should be the earliest block, that is B sub 1. As for Ethereum, we have computed the probability of miners adding blocks conditional to the previous block's miner, and the bottom figure clearly shows that the top-ranked miners prefer to choose their own mined blocks rather than those mined by others. Again, the bottom figure shows the proportion of fork resolving cases with a label showing whether the added block is the earliest propagated one or not. We find only 4 of the top 25 miners faithfully add their blocks to the earliest propagated ones. Due to time limitation, I'll go through other findings very briefly. Another interesting finding is that there are quite large time gaps between the block arrival time and the arrival time of the latest transaction that is included in the block. In this example block, the time gap is as large as 50 seconds. In other words, there are many higher fee transactions which are not included in the block. Instead, low fee transactions that have arrived earlier get included in the block. You can find a more detailed analysis of this time gap in our paper. Lastly, we have observed there are plenty of insufficiently funded transactions in Ethereum network, and even worse, some clients have implementation problems of relaying those transactions. We have reported this issue to Open Ethereum developers and received a bounty reward. This vulnerability could be even exploited to launch a network-wide DOS attack. You can also find more details regarding this issue in the paper. To conclude, we've performed Bitcoin and Ethereum network measurement, and we have reported valuable analysis results, and our key findings include a false assumption of mining research, large block time gaps, and vulnerability of Ethereum clients. Thank you for watching, and please send me an email if you have any questions.